In this video, we'll look at the kinetic molecular theory. The kinetic molecular theory is a model that explains experimental observations about gases under normal temperature and pressure conditions. And so what it really does is tells us how these gases behave and why they behave like that. And so looking at some postulates of the kinetic molecular theory. When we look at the first postulate, it says gases are composed of small and widely spread apart particles. Also, the second one, particles of a gas behave independently of one another. Third, each particle of a gas is in rapid straight line motion until it collides with another molecule or its container. Fourth, the pressure of a gas arises from the sum of all the collisions of the particles with the wall of the container. And fifth, the average kinetic energy of a gas particle depends only on the absolute temperature. So let's look at all these postulates in a little more detail. The first postulate, gases are composed of small and widely separated particles, which are molecules or atoms. This helps explain the volume of a gas, why they have such low volumes of particles. Because in a normal gas, less than 0.1% of the space is actually occupied by the gas particle. The rest is empty space. So if we take a container and we measure the volume of it, gas particles would only be a tiny fraction of the actual volume taken up by that container. This helps explain the really low densities the gases exhibit. There's very little mass or matter per volume here. It also explains why gases are highly compressible. There's all this empty space between the particles. I can smush it together and there'll still be plenty of space for the particles to occupy. Looking at the second postulate, particles of a gas behave independent of one another. So this kind of makes sense. They move independently of each other unless two particles collide. And there's no forces of attraction or repulsion between gases. So again, if we look at our container, in our container, our gases are really far apart from each other. So having one gas move, it's very unlikely it's going to encounter another gas particle. So it's going to move independently until maybe it smashes into that gas particle or it smashes into the wall container. And because there's so much space between each atom or molecule, there's no forces of attraction or repulsion like you might get for a solid or a liquid. And our third postulate said that each particle in a gas is in rapid straight line motion until it collides with another molecule or its container. And then when these collisions occur, the collisions are perfectly elastic. What that means is the energy is transferred from one particle to another with no net loss of energy. So we don't lose energy when it collides. Which means if we So this means when we're looking at our gases, they move in a straight line until it collides, and then it moves in a straight line away from that collision. Or it could be a straight line into it and a straight line back out. The angle doesn't really matter, just as long as it's a straight line. And so the gases are flying in straight lines through their space. What it means is the gas does not kind of zigzag through the space like this. It does not go in a random motion. It's a straight line motion. And when our gas hits the edge or a container, it's going to transfer the energy and it won't lose that energy when it hits the container. Instead, it'll bounce off and continue with the same amount of energy. Or if my gas particle collides into another one, it's going to make that particle move with the same amount of energy that it hit with. There's not going to be a loss of energy when they collide here. Our fourth postulate stated that the pressure of a gas arises from the sum of the collisions of the particles. So this means when we're in a smaller container, we have more collisions, which means we have more pressure that results in a higher pressure. So in a smaller container, our gas particles are more likely to hit the side of the container much more often than if they're in a big container. If they're in a big container, there's more space. So it'll take longer for the gas particle to hit the side of the container. So more collisions equals more pressure. Less collisions equals less pressure. And so our pressure is actually proportional to the number of gases. And we can use the ideal gas law to see this proportionality. Our fifth postulate stated that the average kinetic energy of a gas depends only on the absolute temperature. So we can look at the relationship between kinetic energy and velocity or speed of a gas. So the kinetic energy, the average kinetic energy equals 1/2 the mass times the velocity squared. So the average velocity for a gas particle is greater at higher temperatures. So that means our gases are moving faster at higher temperatures. And if a particle moves faster, it hits the container more often. Makes sense, right? If it hits the container more often, it's going to exert a pressure. It's going to have more collisions. So the faster particle moves, the higher the pressure. So you can see here our temperature and our pressure start to relate to each other. Higher temperatures cause particles to move faster, causing more collisions, which results in a higher pressure. And all gases have the same average kinetic energy when at the same temperature. And so looking at this and looking at the central importance for our kinetic energy, the lighter a molecule is, the faster it moves. The heavier a molecule is, the slower it moves. And our lighter molecules move faster than heavier ones, but they have the same kinetic energy. So they have the same kinetic energy even though the lighter ones are moving faster, because mass plays a part in it. Mass plays a part in our equation for average kinetic energy. So at a given temperature, all gases have the same kinetic energy. The speed of it may change, but the mass makes up for that. So that means for our oxygen, O2 here, it has a mass of 32 AMUs. That's a lot heavier than hydrogen, which has a mass of 2 AMUs. Since hydrogen is so much lighter, its speed is quicker, but the average kinetic energy will be the same as the O2. Its speed may be slower, but it has a higher mass. So that's why H2, hydrogen, is going to always move so much quicker and have a much quicker speed than O2. And you can see the average, and you can see in the graph here the different speeds and kind of the relative number of molecules at a given speed. So you can see here kind of in the middle, oxygen, O2, not that fast. Nitrogen, a little bit lighter, so it moves a little quicker, has a little bit higher speed. Water weighs a little less, so it has a little bit higher speed. Helium has an even higher speed because it's only 4 AMUs. You can kind of think of this as if you're looking at a semi-truck going down the freeway and then a little tiny Jetta going down the freeway. The little tiny car can go much faster because it doesn't have as much mass to move. The semi-truck ends up going slower because it has a lot more mass. And so if we came up with the kinetic energy for both of those, the semi-truck, since it has such a higher mass, doesn't need to move as fast. Its speed can be slower. The tiny little car, since it has a much lower mass, has to move faster to have the same kinetic energy. And so we can use the equation. Kinetic energy is 1/2 mass times speed squared, or 1/2 mass times the root mean speed squared. So the U sub RMS is the speed of the molecule possessing a kinetic energy equal to the average kinetic energy. And so what happens is if we look at the temperature, because temperature affects the speed of our molecules. So at 0 degrees, so if we look at our graph here, at 0 degrees, half of the molecules are moving at a speed, fewer than half the molecules are moving at a speed greater than 500 meters per second. At 100 degrees, so I've heated up, the molecules move faster, more of them are moving at greater than 500 meters per second at 100 degrees. So you can see the curve shifted over when we increase the temperature. So the more molecules here are moving faster. And so the kinetic molecular theory allows us to kind of think about and reason behind all these different gas behaviors and how it relates to speed and collisions, how that can relate pressure and temperature and volumes to each other. And the kinetic molecular theory allows us to examine those.